Hi, my name is Miloš and welcome to Element 14 Presents. Today I'll show you how we went from the robot arm to this whole robot platform with all of the CAD, programming, electronics and everything. Let's go! So if you haven't checked it out before, I've done a deep dive video on the actual robot arm, which you can check out here, but in the end it's just a robot arm. So with this video and this project, my idea is to put that whole robot arm on wheels and add some mobility to it. So let me show you how I actually did that, and then we're gonna go and test it. Welcome back. In our previous video we put together this robotic arm. It works great, but today we're taking it to the next level by giving it some mobility. Let's break down the design for its new mobile base. We are going to mount the arm directly on top of a robust 4-wheel drive platform. To give us maximum control and torque, each wheel will be driven independently by its own dedicated motor. We are designing this with two locomotion setups in mind. Version 1 will use a standard skid steer or tank steering method. Later, for version 2, I plan to swap those out for mechanon wheels, which will give the robot true omnidirectional movement. To keep the build accessible and structurally sound, the main frame will be constructed from standard T-slot aluminum extrusions, held together with machine screws, with a lot of custom 3D printed brackets and mounts. Using extrusion and printed parts is highly intentional. It makes the entire platform modular, meaning it will be incredibly easy to modify the frame, swap out parts or add new hardware as the project evolves. And we are definitely going to add more hardware. Some ideas I have for future upgrades is to add a LiDAR module to the back for mapping and navigation, cliff sensors underneath the front bumper to prevent it from taking a tumble, and a camera with integrated lights up front for remote viewing and computer vision. This is the blueprint. In the next phase we'll start bringing these components together. Stick around and let's get building. Now that you know my plan for this project, let's talk electronics. The whole robot will be based around this board right here. This is the NXP Freedom RW612 development board. It's incredibly powerful, a lot of GPIO capability, microelectronic click here, and it also has Wi-Fi. I will only scratch the surface with what this can do, use Wi-Fi and just some I2C, but it's a really good board and it will be more than powerful enough to handle our robot. Besides that, I'm gonna use some standard DC motor drivers, as you will see, and I will use the popular PCA I2C servo driver, because I need to drive a lot of servo motors, and for driving the geared motors we will also need a PWM signal. So I've said a PWM a lot. Let's check the electronics schematics and then you'll get a better idea of everything that is needed for this robot. All of the electronics will be built around the NXP board, as I already mentioned, and it will have an important job. So my whole idea for this robot is to control it using a joystick like this. This is a Bluetooth joystick that will be connected to my laptop, and I want to send commands over UDP, so over the internet, to the board. Since the board already has built-in Wi-Fi, we're gonna utilize that, and everything will go actually through just the microelectronic connector, the click connector, since it has the I2C lines that we will need. So why do we need the I2C lines? Everything will go through the servo motor driver, since we need to control 4 essentially DC motors and we need to control 5 servos. All of them only need literally just a PWM signal, and this is a perfect board for it instead of going and hunting for pins. The only problem here is the frequencies, since for the actual motor drivers I went with the L298N motor drivers, and they work better at higher frequencies than the servo motors, but at around 300 Hz everything will be happy, both the motor drivers and all of the servo motors. So the electronics are rather simple for this project. Besides that, we're gonna use a battery. As the power supply, I'm gonna use a Parkside 12-volt battery, have an emergency switch as an on-off switch, and just a rather strong buck converter to convert those 12 volts to around 5 volts that is friendly for the servo motors, while the wheel drive motors will get the full 12 volts. So this is all of the electronics. Let's go to the mechanics now. As you've seen, the electronics are rather basic for this kind of a project. We have just one MCU controlling a couple of servo motors and a couple of drive motors for the wheels. But the part where this project was Actually kind of complicated and needed a lot of work was the mechanical part of the project, and you'll see the whole process of this, from CAD to actually the whole time-lapse of me assembling it and wiring it. So let's jump straight into Fusion 360 so you can see how the whole model looks like, and so we can finally build the whole thing and test it. We've done all of the electronics, now it's time for the most complicated part of this project, the mechanical assembly and the CAD. So on the screen now you can see the robot arm that we've made and designed in the previous video. So as the drawing has shown, let's add the frame to it. The frame looks like this. Let me just find it real quick. Here it is. So as I've said, I wanted to make this frame out of aluminum extrusions, the 2020 T-slot extrusions, and this is how I wanted to make it. So it will be a rather strong base, as you can see here, with this thick 4020 extrusion in the middle and used for these pillars. So all of the drive motors will go down here, while the top part will be used for the robot arm, and in between there is a lot of space for any of the electronics. So if we add the drive wheel assemblies, we're gonna do something like this. So each of the wheels will be supported with 2 bearings and an M8 screw. And here you can see how I plan to integrate the motors. I will also experiment with bevel gears, but for now I just used regular spur gears, and as you will see in the end, the results turned out rather okay. Of course, I don't want to leave it like this. We need to package it up around with some plastic pretty much. We also need a way to power it up, so I'm just going to use some Parkside batteries from my drill. And with the outside panels, we will get something that looks like this. So I'm really happy with how it looks like. So this is the version 1, as I've already mentioned. In version 2, these wheels will be replaced with mechanism wheels so that the robot will be even better. Okay, so the only one thing is left to do now, and that's roll the time-lapse and assemble the whole robot. And the robot is finally complete. So it's a rather large robot, it weighs about 7 kilograms or 15 pounds. So currently it has just some standard RC wheels, but as I've mentioned previously, I'm gonna upgrade this to the mechanism wheels, and on top we have the actual robot arm that you've seen in the previous video. Here goes the battery from my Parkside drill. You can swap it out for your style of battery. And I've added here, you can either have another battery, but I added the switch as an on-off switch, and in emergencies if this robot goes wild. As you will see in the video, it has a lot of torque, so it's a rather strong little thing. So the only thing left to do before testing it is to program it, which we're gonna do now, and then we're gonna play around. Before we test the robot, we need to program it. So let's begin with the MCU code. I'm in VS Code here. The NXP MCUs have a VS Code extension, or you can use the MCU Expresso, but I decided to go with VS Code. So what the code for the MCU actually does is it just gets the data over UDP from our joystick that you can see holding in my hand, and sends then the PWM values through the PCA module to the motors or the servo motors. So what it actually does is it connects to a static IP address, this one with the credentials you enter, and from there it parses the data. So let me just find all of the lines of code where we need to go. So yep, here it is. So this is the UDP task, and here we're actually receiving that data, and we just need to handle that payload or parse it. You will see the format in the Python code that's actually sending the data later on, and we parse it with this. this function right here. So it's a byte array that has a length of 20, and from there we just take all of the data that we need. So for the servo motors, we have the 6 servo motors, currently 5 for the robot arm and 6 will be for the gripper, any kind of gripper that we want, that just uses the servo motor, and we have the 2 motor drivers. And in the end, we just send that data over to the module. Here we are. So it's just a while loop where we send all of the data to the servo motors and then send the data over to the motor drivers, where we just do some checks to make sure that everything is within bounds. So that's the MCU code, rather simple. On the computer side or the Python side, we have 2 scripts. We have the gamepad UDP robot sender script and the ARM control core script. So why do we have 2 scripts? The first script handles the UDP communication and getting the data from our joystick, while the other script, the ARM control core script, handles the logic behind converting the joystick inputs to the commands we send to the robot. So it just sends data over to the static IP, the same one that we've configured in the MCU. As for the logic of the controller, now that you can see on my camera, so this left stick here will be used to drive the robot around. As I've previously mentioned, it's a tank drive robot, so when we push the stick to the front, all motors will drive forward and the robot will move forward. If we move it to one of the sides completely, one side will go forward, the other ones will go into reverse, and so the robot will start turning in the spot. Let's go and see that how that works in practice now. As for the robot arm, there is a bit more, let's say, the robotics theory that we need to cover, but you'll see how all of that works later as well. Okay, so our robot is down on the floor, it's fully charged up, or the drill battery is charged up, and we can turn it on. Now I'm going to show you how it actually drives without having any wheels turn. It's not ideal, but you'll see that it works, and as I've mentioned in the drawing, we will be replacing these wheels with actual mechanism wheels. So as you've seen with the joystick, we can go forwards and in reverse, and we can also turn on the spot. Also, if we do this, you can see that it will also move forward while it's turning. So here's just a bit of me driving it around so you can see how it works. The ground clearance is not the best, and it doesn't like the surfaces like the carpet because they are extremely grippy. As you can see how it jiggles a lot. But once we get onto the hardwood floor here, you can see that it's turning just great. Now that will be another issue that we will have with the mechanism wheels, since they won't work good for all of the surfaces, but for wood floors like this, it's honestly working rather nicely. One more thing that we can check is how strong is actually the pulling force on this robot. Since we have 4-wheel drive, I'm gonna attach this scale. The best place I can do is the battery. Let's tear it to 0, and if we pull, I'm getting about 3 kilos, but we're getting a lot of wheel spin. Let's try that on the carpet, since you've seen how grippy that is. Oh, looks like the battery is drained a bit. Okay, here we go. And let's test now. Yeah, this thing is actually doing proper wheelies. But yeah, I've managed to record here in previous tests up to 5 kilos or so, and this thing has 7 kilos if I measured it correctly. So a lot of torque, it can go up some really steep terrain, though with this ground clearance we will keep it down only to flat surfaces. Driving the robot around was rather simple, as you've seen with the differential drive, but what about controlling the arm? One way to control the arm is just move each joint individually, as we've done before, but what if we want to do something a bit more specific? For example, what if we want the robot arm to reach this point like this, or How do we actually even know where the end effector here is located? Now that's called the kinematics in robotics. We have direct and inverse kinematics. In direct kinematics, if we know all of the angles and the lengths, we can know where the end effector is based on all of that data and where our base is. But for us, much more interesting is the inverse kinematics of if we want the robot arm to get here, what are the angles the robot needs to do to actually get there? And is there always a one solution, or are there multiple solutions? Let me explain you that a bit more, since this is an essence of industrial robotic arms. Let's take a look at our robot arm and kinematics. Like any other robot arm, it's made up of a series of joints and rigid links, ending at the very tip, which we call the tool center point, or TCP. The diagram you see here breaks down exactly how the joints operate on our specific robot arm. To do any of these calculations and mathematically control this system, we absolutely need to know a few critical parameters up front. Specifically, we need the exact segment lengths of every physical link, as well as the precise joint angles at any given moment. With those parameters established, there are two main ways we calculate movement. The first is direct kinematics. This is relatively straightforward. If you know the current angle of every single joint and the lengths of your segments, you can calculate exactly where the TCP is positioned in space. You plug in the angles and you get the coordinate position. But in the real world, we usually need the exact opposite. We know the coordinates of where we want the robot's tool to go, and we need the robot's computer to figure out what joint angles will get it there. This is inverse kinematics, and it's where the math gets heavy. To really grasp the level of math required, let's step away from the 5-axis arm and look at a much simpler example, a basic 2-link planar robot arm moving on a flat 2D XY plane. This is called a SCARA configuration. For direct kinematics on this 2-axis setup, the equations are just basic trigonometry. You take the lengths of the two links, multiply them by the cosinus and sinus of your two joint angles, add them together, and you easily find your x and y coordinates. However, to solve the inverse kinematics for this exact same simple setup, the complexity skyrockets. To find the required joint angles based on a target coordinate, you first have to calculate the overall distance to the target, rather simple. Then, you have to use inverse tangent functions like atan2 combined with the law of cosinus just to isolate the angle for the joints. On top of that, the math reveals that there are actually two perfectly valid solutions for the same coordinate, an elbow up or elbow down configuration. If it takes this much heavy lifting trigonometry just to solve the inverse kinematics for a flat 2-link arm, you can imagine the intense matrix algebra and computing power required to drive our fully articulated 5-axis arm in 3D space. Fortunately, because robotic arms have been around for a long time, there are plenty of robust kinematic solvers. We won't be writing all of this complex math from scratch. Instead, we'll be implementing established proven software solutions that handle heavy calculations for us. Understanding this foundation, however, is the first critical step to master robot control. Let's take a look at some code and see all of this in practice on a robot arm. Now that you know what inverse kinematics is, let's take a look at the code real quick. So these are some of the parameters that you need to set up here. As I've already shown you, we need to know the lengths of the linkages. And here I've set up all of the joints, their minimum and maximum angles, so for the servos, the physical angles, as well as the number of microseconds in the on time of the PWM signal, because that's what our joystick script is sending, as you've seen before. All of the stuff underneath is just the inverse kinematic stuff. You'll have all of the codes on Element 14 community if you want to check them out more thoroughly. This is like a bare bones integration, and I've also done one with using just a library, but there is much more to it, as you will see. This will work, but it will be jittery. There's a lot of things like path planning to smooth out stuff, but we won't get into it too much now. One more thing to point out is this calibration file here. So this JSON file stores the default values for all of the joints that they're actually at the physical zero angle. If you take a look back at the robot arm video, when you assemble it, you need to put the servo motor at the 90 degree or the middle point, and when it's in the middle point, then you mount the actual hardware. If you don't do that, there will be a lot of errors that will just add up, and there is just a function to actually calibrate the arm, so you tell it where the actual zero position is. For controlling the arm with the joystick, you'll be using the D-pad here. and the right and left triggers here. So with this here, you can set the coordinates that you want your TCP to reach in the XY plane, and with this you adjust the Z-axis. If you press both buttons at the same time, you enter the calibration mode where you do as you see on the screen now. You set up those angles, and if you press all of these buttons, you enter the jog mode where you can actually control each joint separately without caring about kinematics. One more thing that I have to show you is the visualizer script, which is this. And if we run it now, let's just wait for it to start. Okay, here we go. So what this script does is actually show you the simulation of what the actual robot arm would be doing. So for example, if we press the left trigger here, this will lower the Z coordinate, and you can see in 3D and both on the side view how the arm wants to go down. If we go on the D-pad and try moving the X-axis, you can see how it tries to move along only the X-axis while keeping all the rest constant. And you can see that there is some jerkiness to it. So as I said, there is a lot of path planning that should be involved here as well. But for just some simple tests to see how it works and for you to understand how what's kinematics, direct and inverse kinematics, this is a pretty good demo, and you'll see how all of this works on the actual robot arm now. You've seen how the arm looks in the simulation, but let's see how everything works in real life now. So as you can see by the blinking green light here, the MCU is on already and it's connected to the joystick that I have in my hand. So let's just turn on the power, and you can see the arm is in some random position. Now, if we try going, for example, up or down, you can see that the movement is kind of weird, and that's because I've deleted the previous calibration file. So let's enter calibration mode so you can see what actual calibration does. So this is calibration mode, and in this mode, the robot arm is actually in what it thinks is a completely upright position. But obviously it's not, and that's due to error when assembling it. You can assemble it better than me, but let's go and calibrate it so we can actually test it properly in software. And here you can see I can adjust joint by joint. So let's do that. You can go to one or the other side. This looks okay. Next one. Like that. Next. Like so. Like that, and that should be it. So as you can see, this is the new base position, and now if we try going down, while it's still jittery, you can see that the robot arm is going perfectly up and down. Now if we try going just along the X-axis, which is the front of the D-pad, you can see how it's trying to hold that position until it reaches the singularity for that. And also if we go back, you can see it will try doing that. If you try going much more further back, it will actually fail because the base can't turn by 180 degrees, and it also works if we go to one or the other side. So you can see how it goes in a straight line, and if we go to the other side, this part of the movement is rather smooth, and that's because the inverse kinematics are rather nice even without any path planning. But for example, for the Z-axis, if we go, there are some moments when it's kind of jittery, like there, for example. But yeah, you can see that it's all working now even in real life. So the only thing left to do now is combine the test between the robot arm and the platform itself. You can see the whole robot now on the table, and now we're gonna test both the arm and the platform. So you've seen them work separately, but now if we try, we can control both of them actually. There isn't a lot of room on my table, but we can still drive it around. So we can lower the arm like that. We can of course do those at the same time as well. I'm just trying not to drive off the table because that would be a a rather loud boom since the robot is so heavy. But yeah, it's actually really maneuverable on hardwood surfaces like this table or the floor as you've seen, and it's rather easy to control since the motor stops spinning instantly because of the gearing once you let go of the controls. And for example, for the Y-axis you can see that the inverse kinematics are working rather nicely. So we can get it close to the edge. We can work with the robot further. The kinematics can do with a bit more work here, so we can actually go underneath the robot surface and so on. Now that we know that everything works on this robot here, it's time to actually do something practical with it, and we're gonna use this for it. So this plate here has a bunch of holes that are threaded for M4, so you can add either grippers or something like this. This seems just like a small cup, but it perfectly fits the amount of dog feed that my little puppy needs. So let's try and feed my dog with this thing and see how she likes it. If she does, maybe this can become a routine and I can automate it, but as you will see, she's not too fond of it yet. Thanks so much for watching the video on my progress with this robot platform. I'm really happy with where it is now, and I can finally start doing some more serious things with it. Next step is to actually add an embedded computer to it, something like an NVIDIA Jetson or a Raspberry Pi, so I can run ROS on it, or ROS2, we'll see, so I can do some more advanced stuff, STEM algorithms, but we're gonna have a rather nice platform for it. Once I add the mechanism wheels, we can really do some cool stuff with it moving around, also pairing that with the robot arm simulations and everything like that. If you have any ideas for what you would like to see actually done to this platform, please let me know, and you can also find all of the files available for free on Element 14 community. Until next time, see ya!